Good afternoon, class. We are looking at Chapter 4, Application of Derivatives, Section 4.2, How Derivatives Affect the Shape of a Graph. We covered maximum and minimum values, and now we're going to go to how derivatives affect the shape of a graph. There are many differentiation formulas here. We should be very comfortable to be able to move on with the reverse process later on. Delta y versus dy is explained here. Delta y is the rise along the curve. Dy is the rise along the tangent line. And if we give this point coordinates a and f of a, using the point slope y minus y1 equals m times x minus x of 1, we can find the linearization, which is known as the tangent line. You don't have to memorize this formula, just stick with the point slope and it'll do the job. Maximum and minimum point on a curve for relative extrema, local mean, local max, local mean, local max, they occur in some open interval. Absolute, also known as global extrema, they occur in the entire domain. So, local mean, local max, local mean, local max, local mean, local max, local mean. This one is also absolute mean. Local max, local mean, local max. This local max happens to be an absolute also because it takes place in the entire domain. There is no other point having a larger y coordinate. Definition of a critical point: a critical number or point of a function f is a number c such that f prime is either 0 or does not exist. The process is to find f prime of x, set f prime of x equal to 0 or f prime does not exist. The extreme value theorem or closed interval theorem method, it applies to a continuous function in a closed interval of a to b. First, we find the CPs, critical points, by setting f prime equal to 0 or does not exist. Then we evaluate the function at the end points a and b as well as the critical points. The absolute maximum is the largest value and the absolute minimum is the smallest value. Now we're going to go to the summary of this section 4.2, how derivatives affect the shape of a graph. A theorem: a function is increasing where f prime is positive and decreasing where f prime is negative. Think about this curve. Imagine that it's a line. This is a line with a positive slope. This is a line with a negative slope. A critical point C of a function is a point for which f prime is either 0 or does not exist. A relative maximum or relative minimum is a critical point at the top or bottom of an interval of a graph. A function is concave up where f double prime is positive, at which case f prime is increasing, looking like that. It can hold water in essence. A function is concave down where f double prime is negative, less than 0, which means f prime is decreasing, looking like that. It cannot hold water. And it gives rise to the definition of an IP. An inflection point or IP, C, is a point where concavity changes. Inflection points occur where f double prime is 0 or f double prime does not exist. The end. So this is the location where the change occurs, in this case from concave down to concave up. So going back to this concept of concavity, concave up, the graph of the function f of x lies above all its tangent lines on the open interval. If you look at these two cases, if you just look at one tangent line, concave up, it's above the tangent line, concave up is above the tangent line. However, concave down, the graph of f of x lies below all of its tangent lines on an open interval. So as you can see, this one is below the tangent line, this one is below the tangent line. So if we have a couple of it, you want to notice the following. For f double prime being positive, f prime is increasing. Here's the reason. If you look at these two line segments that they represent tangent lines, both of them have positive slopes, but this one, the slope is less than this one. This is steeper. Whereas in this case, both of them are negative, but this is steeper, so this is more negative. That's why f prime is increasing in those cases, at the same time above the tangent lines. In these two cases, f double prime is negative and f prime is decreasing. Notice, for example, this one, this has a negative slope, this has a negative slope, and it's steeper, therefore it has a more negative slope. Positive slope, positive slope. This one has a larger value than this one, so that's why it's decreasing. And a point P on a continuous curve f of x is an inflection point if f of x changes concavity. Here, for example, here from concave down, it goes to concave up. This is a point of inflection. From concave up goes to concave down, IP, or the point of inflection. So what are the steps in curve sketching in addition to what we learned previously in algebra and pre-calculus? Number one, find the relative maximum or minimums and intervals where the function increases and decreases. To do so, you set f prime equal to 0, solve for x, and make up a sign graph, a number line, and test values between critical numbers. Find inflection points, set f double prime equal to 0 and solve for x, and again do a sign graph. Find possible inflection points or IPs and where the function is concave up or concave down. Finally, put all of this information together and sketch the graph. Extreme values of the function are created when the function changes from increasing to decreasing or from decreasing to increasing. So in this case, it's increasing, decreasing, and at the top we get the extreme value. In this case, decreasing, increasing. At the bottom we get the extreme value. In this case, decreasing, increasing, decreasing. At the bottom and at the top we have the extreme values. Again here, increasing here, decreasing here, increasing, decrease. At the bottom we have extreme value. At the top also we have extreme value. And of course, the concept that gives rise to a local max here versus local mean. But what we want to discuss, we want to remind everybody, a function is increasing where f prime is positive and is decreasing where f prime is negative. I want to quickly show you the proof. You're not responsible for that. There is something called the mean value theorem, which indicates if f of x is a continuous function in the closed interval of A2, and f is differentiable on the open interval of A2. If you connect the endpoints A and B, it creates a secant line with a slope of f of b minus f of a over b minus a. There is some point C in between the 2 points that has a tangent line parallel to that, so therefore it has the same slope. Cross product gives us f of b minus f of a equals f prime of c times b minus a. As far as the mean value theorem is concerned, sometimes they write it in this fashion, sometimes they write it in this fashion. I hope you see that this creates this one. So stick with this one, for example. Also, increasing in short means when x gets larger, so does y. So in other words, if you go from left to right, x gets larger. If the y gets larger, that means increasing. So clearly, the way we have chosen, let b larger than a, okay, greater than a, because b is on the right side. If f prime of x is positive, that means f prime of c is positive, because f prime of x is a general form. And if f prime of c is positive, that means this fraction, f of b minus f of a over b minus a, must be positive. Now, if this fraction is positive and b is larger than a, the denominator is positive. So the numerator must be positive also. So if b is larger than a, f of b must be larger than f of a, which is the precise definition of an increasing function. What is the first derivative test? Y prime or f prime is larger than 0. The curve is rising. First, when it's looking like that, it's increasing. The function is increasing. And then if it's less than 0, the curve is falling, looking like this. So it creates an extreme. This is a local max. As it changes from increasing to decreasing, creates a local max. On the other hand, if we start with f prime being negative, curve is falling first, looking like that. And then it's positive. Curve is rising now. Again, it creates a local extremum, but this time is a local mean. So as it changes from increasing to decreasing, gives us local max. As it changes from decreasing to increasing, gives us local mean. And the process is to find y prime or f prime, set it equal to 0, or where it doesn't exist. So those are possible local extrema, local maximum or minimum. So what is the process of finding it? We are going to use sign graph for this test. Concavity test. Y double prime, we go with the second derivative. If it's positive, curve is concave up. If it's negative, curve is concave down. If you recall, we said in pre-calculus, concave up, it can hold for a concave down, it cannot. And where it's 0 or does not exist, that's a possible inflection point where concavity changes from one format to the next, concave up to down or vice versa. A function is concave up where f double prime is positive, which means f prime is increasing, and a function is concave down where f double prime is negative, which means f prime is decreasing. Now, we don't want to mix this up, and the process is to use the sign graph for this test. We don't want to mix this up with the second derivative test. Second derivative test uses the second derivative, and sometimes people confuse the two. So basically, you're going to evaluate f double prime at CPs, critical points. So when you plug in the values that you found into f double prime, if it happened to be negative, that means the graph is concave down. Looking like that means what? This is a local max. So x equals CP is a location of a local max. On the other hand, if it's positive, graph is concave up, looking like that. This is local mean. So x equals CP, the critical point, is a local minimum. That's the location. In order to help us graph, I want to remind you of a couple of things. One of them is the end behavior. Recall, The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 1 x plus a sub 0. This will ultimately look like the leading term. This is the leading term, a sub n x to the power of n. So when we are dealing with even powers, if a sub n is positive, looks like this. If a sub n is negative, looks like this. And if we are dealing with odd powers, a sub n is positive, looks like this. A sub n is negative, looks like this. Meaning, this looks like x squared. When x goes to negative infinity or positive infinity, y blows up to infinity in both cases. In this case, when x goes to negative infinity, or positive infinity, y goes to negative infinity. That's why we have those. Over here, in this case, it looks like x cubed. In this case, it looks like minus x cubed. In this case, when x goes to infinity, so does y. When x goes to negative infinity, so does y. In this case, when x goes to negative infinity, y goes to positive infinity. When x goes to positive infinity, y goes to negative infinity. So it is explained here. We also have a theorem, behavior near a zero multiplicity m. A zero with x minus c to the power of m has a multiplicity m. If m is odd, f crosses the x-axis at c0. If m is even, f does not cross the x-axis at c0. So in this case, we have a single zero. In this case, we have a multiplicity 3. Both of them are odd, so they cross. In this case, multiplicity 2, for example, y equals x squared, it cannot cross, it bounces back up. The higher the multiplicity, the flatter the curve is at the zero. The sum of the multiplicities is the degree of the polynomial function. So I thought it's worth reminding everyone as to how we did the graphing previously. And so for this example, I want to use that information and graph it, and then we're going to add calculus to make it look better. Just the way it is, we are going to find the intercepts first. So example 1, graph y equals x cubed minus 3x squared plus 4. In a factored form is x plus 1 times x minus 2 squared. You have to go through the process of factoring it. This format easily gives us the y-intercept at 0, 4. This format gives us the two x-intercepts, -1, 0, +2, 0. So I'm assuming everybody is comfortable with that. We are going to graph this using just this knowledge that we have. So we are going to go with -1, 2. To 0, 0, 4. This means it will ultimately look like y equals x squared, x cubed, the first and the third quadrant. That's the end behavior. When we look at this x-intercept, we notice the multiplicity is 2. So I'm going to put an arrow here, meaning it can't cross that. So if we were to graph it, it looks something like this. It hits this x-intercept, it comes up. How far it goes, we don't know, but it has to hit this y-intercept and then this x-intercept and goes through it. Now, how does it look like as far as over here is concerned? It may just go to the y-intercept and come back down. It may hit the y-intercept, go further up and come back down. We don't know what happens here. We don't know where the function is increasing, where the function is decreasing. So that's why we are going to use calculus. So this is the shape of a graph. Roughly, we know that from previous knowledge of algebra. But let's make it more precise. We want to find the relative max and mean. So we need to find the derivative y prime or f prime of x is 3x squared minus 6x. We're going to set this equal to 0. To do so, we factor out the 3x. We get 3x times x minus 2. Either x is 0 or x is 2. So there are two possible solutions. By the way, to find the critical points, you look at f prime or y prime, say where it does not exist because it's a polynomial of degree 2, it exists everywhere. And now we are going to use the first derivative test by using a sign graph. Here's how the sign graph works. You have a number line from negative to positive infinity. You put the critical points in order from smallest to larger. So 0 goes here, 2 is here. At 0, f prime or y prime is 0. At 2, f prime or y prime is also 0. And now you use TPs, short for test points. I'm going to call them TPs. Test points. So in between 0 and 2, for example, 1 to the left of 0, negative 1 to the right of that, 2 is 3. Those are the TPs, test points, meaning what? Put this into f prime or y prime, put this into that, put this into that, see what happens. Now, one thing I want to make a point of, if you go back to the fact that from this has exponent 1, this has exponent 1. So as long as you get one of them, the rest of them alternate. For example, if I put 1 in here, I get 3 minus 6, which makes this negative. If you put it here, you get positive times negative, which is negative. And they will alternate, or you just can put negative 1. If you put the negative 1 here, becomes positive 1 times 3 is 3 minus 6 times negative 1 is positive 6. So this is positive. As I said, it is going to alternate, but you can check. Let me throw in arrows, positive arrow up, negative arrow down, positive arrow up. So it will help us see what's happening. So as it changes from increasing to decreasing, it gives us local max. As it changes from decreasing to increasing, it gives us local mean. So local max and local mean. Local max occurs at x equals 0. Now you got to put that into the original function. If I put the 0 here, of course, you already had this point. So you are going to say local max equals 4 at x equals 0 or at the pair, however they ask you. Local mean, you plug in the 2 into the original function. 2 happen to give us 0. So local mean is equal to 0 at x equals 2 or 2 comma 0. As I mentioned, positive means increasing, negative means decreasing. So the function is increasing from negative infinity to 0, union 2 to infinity, and it's decreasing in between 0 and 2. So we got a lot of information here, everybody. So the first derivative test gave us critical points, local max, local mean, intervals of increasing, decreasing. Now, this is the function This is the first derivative. These are the possible CPs, everything from the previous page. Now I want to use the second derivative test, and I want to remind you f double prime positive means concave up means relative mean. If double prime is negative means concave down means relative max. We are going to use that. You don't have to do this. We've already gone through that, but I want to show you how it works. So first and foremost, take the derivative and we get the derivative again because we are going with the second derivative, 6x minus 6. Now you're going to evaluate this at 0 as well as 2. So if I plug in 0, I get negative 6. In other words, negative. So I'm here. When it's negative means concave down. It means relative max. So at x equals 0, you have a relative or local max. So what do? You plug in 0 into the original function, which gives you the pair 0, 4. So graph is concave down, looking like that. Concave down means what? Up here we have it. Local max. Very straightforward, everybody. Now, if we plug in number 2 into y double prime, we get 2 times 6, 12 minus 6 is positive 6. And positive 6 means concave up, looking like that. So what is that? Local mean. So graph is concave up, local mean at x equals, so of course again 2 has to go back into the original function because you want to find the pair. Now, what I want to add is very simple. Please do not use the second derivative to graph. Okay, why is that? Because it gives you half of the information of the first derivative test. Okay, in the first derivative test, not only we find local extrema, we also find intervals of increasing, decreasing. So why are we learning the second derivative test? Because when we do the applications, in many cases, it makes it easier. Now let's continue. We have this function, we have its derivative, and we have the second derivative. We all found all of it in the previous part. So we are going to use that. And now, of course, we are going to go with the test of concavity. When f double prime is negative, it's concave down. When it's positive, it's concave up. So let's set this equal to 0 and solve. And of course, x becomes 1. That's a simple case. We go with a number line because a possible inflection point takes place at where y double prime or f double prime of x is 0 at x equals 1. So we go with a number line from negative to positive infinity, x represented there. And this is f double prime or y double prime. And over here, we're going to put the number that we got here, 1. At x equals 1, the second derivative is 0. So what do? We're going to do the test point. Clearly, to the left of 1, an easy number would be 0. We are going to put the 0 into that. We just want the sign. When we plug in, obviously becomes negative. And when it's negative, it means concave down. If we plug in a test point to the right of 1, for example, number 2, we get 2 times 6 minus 6 is positive 6. Positive means concave up. So negative means concave down from negative infinity to 1. Positive means concave up from 1 to infinity. Because of the change, whether it goes from negative to positive or positive to negative makes no difference. Because of the change, x equals 1 is the location of a inflection point. So what would be the y coordinate? Plug it back in. So if I put the 1 into this function, however, you can go here, 1 cubed minus 3 times 1 squared plus 4, which is 1 minus 3 plus 4, which is 2. And so we found the inflection point, or IP. Okay, everyone? Really nice and easy. Now, every piece of information in the previous pages, we're going to put it here. For example, here's the function. Here's y prime. Here's y double prime. Here's the intercept, increasing, decreasing, concave down, concave up, IP. This information comes from the previous pages and what we worked out. Let's make a summary table of these pairs and let's plot them in. Minus 1, 0 is right here. 0, 4 is right here. And because it's a maximum, we are going to use a double arrow, meaning the graph can't cross that. The IP takes place at 1, 2, somewhere here. The x-intercept, the second one, is located at 2, 0. And because it's a minimum, we're going to have a double arrow again, meaning it can't cross that. You really have the end behavior, the first and the third quadrant. You don't need to pick extra points. But if you pick 3 and you put it into this one, it's probably easier to calculate. This gives you 4, 3 minus 2, 1 squared is 1. So 3, 4 is another point. You know the shape because of the end behavior looks like that. And I hope you recognize everything is there. The intercepts, the 2x intercepts, the y-intercept, local mean, local max. The graph is increasing, then becomes decreasing, then increasing. Inflection point, see it's concave down, then concave up. Every piece of information here, you can see it in your graph.